Okay, this is a lecture on optimization and optimal control. Basic overview plus some illustrative examples and applications in radiation transport. In the introduction, I'll just talk basically about two methodologies. In optimization, you can either use the deterministic methodology or the stochastic methodology. In the deterministic methodology, which is very common, Newton's calculus is used. In derivative-based methods, the Euler-Lagrange formulation is used in the variational methods, and in the so-called bang-bang method, Pontryagin's maximum principle is used in a kind of discretized control formulation. In the stochastic methodology, there is the Monte Carlo method, which can be used to solve equations, or it could be used as an analog simulation of a process. There are heuristic stochastic optimization techniques such as genetic algorithms, particle swarm optimization, simulated annealing, etc. So there are two methodologies, deterministic and stochastic. Calculus is associated with Isaac Newton at the University of Cambridge, followed by the work by Euler and Lagrange years later in France, who are credited with variational calculus. Then for the kinetic theory of gases, Ludwig Boltzmann developed the Boltzmann transport equation, which is used for radiation transport problems, for fluid mechanics, plasma physics, wherever you have n-particle transport. By n-particle, I mean neutrons, charged particles, X-rays, gammas, electrons, etc. An advancement in variational calculus was given by Lev Pontryagin, who passed away in 1988. So the chain of calculus can be thought to begin from the work of Newton to Euler-Lagrange to Pontryagin, and it's applied so extensively in science, engineering, and extends into other areas such as finance and forecasting. Calculus is concerned with the optimization of a function. For example, if you're given a function of x like x squared, then you could find the first derivative. And if you have more than one variable, you could you could say the partial derivatives are zero. You could find the turning points and apply the second derivative test in the Hessian matrix to determine the nature of a turning point. Now, in the variational formulation, we talk of finding a best function. So a function of a function, which is called a functional, is extremized. Now, in Euclidean geometry of planes, a geodesic is the shortest distance between 2 points. The example is that if you look at the distance between A and B on a flat surface, then you would find, applying Euler-Lagrange equation, that it's a straight line. And this is one of the classical problems of variational calculus. Similarly, in spherical geometry on a sphere, if you were to find a geodesic, it would be the great circle, which goes through the whole sphere on the surface, for which the azimuthal angle is a constant. Some application areas of optimization in engineering are electromechanical systems, fluid and hydraulic systems, where you could formulate using the mass spring damper model. You could find the force in a muscle robotic arm to minimize the energy used of a battery, or to complete a required mission in minimum time. You could use it for a mobile robot, such as a drone. You could follow a reference trajectory with minimum error. You could use it in radiation transport systems where, as I just mentioned, the Boltzmann equation L phi is equal to S is a constraint, and you could use the boundary conditions to extremize some reaction rate of interest, sigma I phi, where capital sigma, the macroscopic cross-section, is the product of the number density, the spatial distribution of the atoms or material or mixtures such as water, steel, fuel, multiplied by the microscopic cross-section sigma I. Now the objective in such optimization problems is to find the optimal distribution n. In finance, also variational calculus is used with equal importance. As in science and engineering, you could find optimal strategies for investment. So in variational methods, you would solve the Boltzmann transport equation for a radiation problem, then use Euler-Lagrange. It is a good, elegant theory. It is restricted to simple formulations and limited in application. Pontryagin work was found to be easier than that of Euler-Lagrange, but variational methods are limited in scope. You could also couple deterministic methods with stochastic methods, such as coupling finite difference, finite element methods with a heuristic method, such as genetic algorithms. Another option would be to use stochastic methods such as Monte Carlo simulation. Now, these are very good for full 3D, large, realistic problems, but they're very time consuming. They're good for high performance computing. They're inefficient for repeated simulations. And so people think that they're not useful for optimization, but you can use Monte Carlo with perturbation methods, which have been developed and which can be used for optimization. Now, let me give a simple example, which is very useful to understand in a simple model. And this is taken from this reference over here, that you have two coupled first order ODEs. X1 dot is X2, X2 dot is minus X2 plus a control U of t. The boundary conditions are that X1 and X2 at 0 are 0, and X1 and X2 at time 2 are 5 and 2. We want to carry out an optimization. We want to find an optimal function U of t, which extremizes a functional j, which is going to be a function of our function, which is the optimal control. So here are the steps. We first write the state space equation. We formulate the performance index. We write the Lagrangian. We apply the stationarity conditions, and we solve for the co-state or adjoint variables using the adjoint equations. And finally, we solve for the optimal control U star. So for this problem, we can write the Lagrangian L as half U square plus the Lagrange multiplier lambda 1 multiplied by F1 plus Lagrange multiplier lambda 2 times F2. Now the constraints, there are two constraints in this problem. Therefore, we have two Lagrange multipliers. The state equations tell us that x dot is the partial derivative of the Lagrangian with respect to the Lagrange multiplier. Now both these equations give us the state equation, so we do not learn much from them. The next are the co-state or adjoint equations, which are minus lambda dot is the partial derivative of the Lagrangian with respect to x. Now that gives us two equations, the first for the adjoint function lambda 1 and the other for lambda 2. Both are first order ODEs. Finally, the optimality condition requires the partial derivative of the Lagrangian with respect to u to be 0. So if you look at the Lagrangian, there's only a u over here, and there's a u in F2 because F1 does not have a u over here. So we get two terms. From the first, we get u, and from F2, we get u multiplied by this Lagrange multiplier outside. So it's just lambda 2. So from here you can see that the optimal control u star is just minus lambda 2. Now we solve these equations. So you can see over here that lambda 1 dot equal to 0 implies that lambda 1 is a constant. Then you can solve for lambda 2 in terms of two constants. You could use the partial L, partial U to get U star. So we have found the optimal function U, which is U star, and we need to determine the constants. So if you put this U star in the state equations, you can find x1 star, x2 star. So now we have all the functions required for extremizing our functional. Now we've got 4 boundary conditions. As I mentioned over here, that we've got 2 boundary conditions over here for x1 and x2, and we've got 2 boundary conditions here at the final time. So at the initial time we have 2, at the final time we have 2. I could also have attempted to use the transversality condition to get the adjoint functions, but it turns out that in this problem the initial and final are both given, and so that's not easy from the transversality conditions. So we apply the x1 and x2 4 boundary conditions to get the 4 constants c1, c2, c3, and c4, and the functions that are obtained are shown in this figure. That this is x1, the red one, x2, the blue one. So you can see that they satisfy this boundary condition, that both are 0 at time 0, and over here they x1 over here is 5, x2 over here is 2. The green one is the optimal function which we were trying to get. This over here is the adjoint function lambda 2. Lambda 1 is not shown because it is a constant. It has a value minus 7.2918. So the best value which is found of j of u star using the solution is 16.7507. Now you could use Matlab with the symbolic computing option, and this is the program which you can run. So you would declare your symbols x1, x2, the 2 Lagrange multipliers, the control function, the performance index. You could model your state equations. This is x1 dot is x2 and x2 dot is minus x2 plus u. So these are the 2 state equations. This is the performance index. G is half u squared. This is the Hamiltonian or the Lagrangian. And this is the first derivative of lambda 1, first derivative of lambda 2, which is partial Hamiltonian with respect to x1, partial h. Now the terminology Hamiltonian and Lagrangian imply the same thing in this formulation. And so similarly, the equation for optimality is du equal to partial dh by du. And you can solve the equations. There are 4 equations over here, equation 1, 2, 3, and 4. Now this uses the dsolve command of Matlab to solve these 4 equations with these 4 boundary conditions. Now this is the command, and to recover your x1, x2, and p2, so you do a sol underscore a dot with the variable that you're trying to recover, to retrieve. You convert x1, x2, and p2 with the Matlab function. And so this is what I did, that I evaluated the functions and plotted them. The result that I showed over here was obtained by using both symbolic computing and by a straightforward Matlab program, which you can see that you solve the equations as I showed you. The 4 constants C1, C2, C3, C4. So you can just copy this program from here and run it, and you'd get the same result. Now, let me take you to another problem, the mass spring damper, which is so extensively used in science and engineering. So this is Newton's second law of motion. F is equal to ma. There's a viscous damping term here. There's a spring term. F is minus kx. So this is Hooke's law. This is viscous damping. And so you could formulate this again in state space with the two variables x1 and x2. And as done previously for the same boundary conditions, I ran the program again, and you can see that this is x1 and this is x2. Again, both of them satisfy the boundary conditions at 0 and 2, and we have an optimal function u over here. So that completes the illustration on the use of the Lagrangian for state space coupled ODEs. Now let's see what applications there are to n particle transport. Over here, by n particle, as I mentioned before, I mean neutrons, alpha, beta, gamma, electrons, X-rays, gamma rays. And one code, for example, MCNP, is extensively used, developed at Los Alamos. It's now probably the third or fourth generation. It is a production code and has very successfully demonstrated that it's almost as good as running an experiment. There are two kinds of problems in nuclear systems, for example. There are fixed source systems and multiplying systems. Now, in fixed source systems, which means that there's no fissile material or fertile material, you would maybe be challenged by finding a best moderator design, or to design a radiation shield, which could be a composite or it could be multi-layer shield to protect from neutrons, gammas, for example, in a hospital during an X-ray, or in brain cancer therapy such as BNCT. So there, the source design would require optimization, meaning minimum weight of a shield, minimum space used by a shield. Then in fusion blanket design, this is another very important, because as you know, fusion reactions give out neutrons, and neutrons can be used to breed tritium from lithium in a blanket which surrounds, for example, the ITER tokamak. If you look at www.iter.com, the International Thermonuclear Experimental Reactor, you'll find a fusion tokamak where confinement is being tried for full-scale power. Now, in the present day nuclear reactors, which are multiplying systems, or in experiments which have uranium, plutonium, or fissile material, so these are all called multiplying systems. Here, there's a lot of application in nuclear reactor design, in fuel management, in the way that you could distribute fuel, variable enrichment fuel. You could look for minimum mass for space reactors in future. And you could distribute the fuel so that you get a uniform power distribution. You could minimize the flux peaking. This is a very important area in reactor design and operations. And now, just to give you one example of a fixed source problem. Now, this is let's say this is an explosives detection system as a fixed source system with thermal neutron activation analysis. So there are lots of mines. For example, if you have TNT explosive hidden under soil, how would you detect it? You would fire neutrons on it, you would activate. A TNT would typically have carbon, nitrogen, oxygen, and hydrogen in it. So from the reflected neutrons and gamma rays, you could pick up the signal and identify an explosive. In a nuclear reactor, now this is a cylindrical reactor, as most reactors are. So this is, you could say that you could divide the core into two regions. One is the inside cylinder, one is the outside cylinder. And you could determine the criticality in a two-zone bare cylindrical reactor. You could find the optimal distribution of fuel to minimize the amount of U235 required for criticality. A very interesting application is for a micronuclear reactor, for modern small power systems being developed for microgrids and for space applications. Now, this is a picture which shows you what could come in the next 5 years. Westinghouse, for example, is developing the Evinci micronuclear reactor, which could go on a trailer. You could transport it to any location that you would like to provide electricity to. So these are very safe, futuristic systems, not too distant in the future, maybe in the next 2-3 years. NewScale is another company which is successful in this area. And if you look at this picture, the space missions. So this is an artist's impression of a space station where you could have 4 power plants and you could have houses where people would be inhabited on Mars or the moon or planets that human beings go to in future. Now, this is a person standing next to a little nuclear propulsion system or nuclear space station. Now, for deep space explorations, you can see this little nuclear reactor over here. That's the nuclear part. And these are the fins for heat removal. This is a shaft. And this is where, for example, you could have a heat pipe and you could have a thermoelectric generator producing heat, and this could be the electric supply system. This is a small nuclear power setup using highly enriched fuel plus beryllium oxide radial reflectors. So these are all promising areas where you could use optimization very effectively. Now, presently what is being done is that the same Lagrangian which I introduced earlier is being used in what is called a two-group formulation, which are basically two coupled ODEs which convert into 4 variables for state space, 4 state space equations. And the previous problems that you saw for illustration were simple because the control variable u was separate. Now in these kind of problems, u is not separate, it's inside. So it's not as simple as what I just showed you, but the idea is the same and the methodology remains the same, that you use the equations, you cast them into a Lagrangian form, and you try to obtain stationarity conditions which help in obtaining an optimal solution. Monte Carlo simulation, I mentioned that you could also do optimization. Now it was von Neumann who interpreted analog simulation to be something like an integral form, which Volterra and Fredholm formulated earlier for the collision density chi. P is phase space 7 variables as a direct source contribution plus an indirect contribution. So the kernel K going from some phase space P prime to P is made up of a collision and a transport kernel. The collision kernel shows that for group G prime, now here, as you can see, is a collision. The neutron comes and hits a nucleus. The neutron goes there, the nucleus goes here, and you have the lab system or the center of mass system. So you've got energy transfer. So you go from one energy group to the other, you change your angle as well, and then the particle is transported at the new energy and new angle and goes to another location. So the idea here is to find the flux, and a very commonly used estimator is the so-called track length estimator, which measures the distance between collisions for a statistical weight Wi, total weight W, and volume V. You could also find the current Js, and you could easily find the flux. So perturbation theory makes it possible to use a Taylor series type expansion, where you could get first derivatives of C and T and cast them in the form of a derivative of K. And so you could also estimate the change in flux in all the group fluxes from a single run. So that makes Monte Carlo simulation with the perturbation analysis ideal for a full realistic 3D problem um, in which an optimal design is required. Now, this is the flow chart of a Monte Carlo simulation. You start, you define the geometry, materials, which can be full 3D using combinatorial geometry, Boolean algebra with surfaces. You begin a batch, you begin a history. A history consists of a series of random events, and you start a source particle, you process the collisions, update your tallies till it's captured or it leaks from the area of interest. You continue simulation until you reach the end and you process your tallies and come to the end of the simulation. Now, in fixed source problems, as I told you, it's the Boltzmann transport equation, which is an integral differential equation, which is difficult to solve with 7 variables. So that is the constraint condition. And since it's not possible to do that, so we resort to what is called a multi-group diffusion equation, which is shown over here. That's also difficult. And so in an elementary analysis, we carry out a 2-group diffusion equation. But for reactor design, the multi-group diffusion equation is extensively used. In multiplying systems, the Boltzmann transport equation, in addition to the previous terms, has a fission possibility represented by sigma f multiplied by phi. Chi e is the fission spectrum of fission neutrons emerging from the fission, which find themselves in the phase space of interest for which this equation is written, the R omega E. Now, this is the steady state Boltzmann transport equation. Again, as previously, the 2-group diffusion equation over here is simpler to use for academic purposes, for preliminary optimization analysis. It's a very useful equation. Now, another method that I would like to very briefly go through is genetic algorithms, which is shown over here, that you start on carry out a simulation, generate a population, calculate the fitness of a chromosome by calling the function of interest over here. So you make several calls over here and you calculate the fitness. In other words, how good is every member of your population. And then the survival of the fittest, you select the best chromosomes. This is Darwin's theory of evolution, but this is what he thought nature follows. And so you, from the good, best chromosomes that you found, you carry out a crossover, mutation, and you obtain the next generation. See if the solution is converged. If yes, then you've got your solution. Otherwise, you go in the iterative fashion to carry on until an optimal is found. In nuclear systems, you could find the best design parameters, such as fuel enrichment, the size of fuel, the pitch, the spacing, the materials, and you can iteratively get an optimal design. Now, here are some references. A very useful point to start understanding optimal control is a book by Lewis, Farabi, and Sirmos, which I use for teaching this course at the MS PhD level, and a little bit of exposure to advanced undergraduate students. Then there's Bell and Gladstone for nuclear reactor theory, Lamarche, Carlos, and Whitlock, CNP code described by Briesmeister, Handbook of Nuclear Engineering, and this is a very old but very useful, good collection of theoretical methods on variational, on optimization by variational methods by Den. For genetic algorithms, you have codes available in this book by Haupt and Haupt. Publications, these are useful publications. My first publication in this was in 1990, where I tried to understand 2-group Monte Carlo perturbation theory. So a useful point to start from is Qureshi and Lewins, my professor at Cambridge, with my PhD supervisor. This is a very old first application that I saw of Pontryagин's maximum principle. Dr. Reef is the man who made a huge contribution, who I had the honor of meeting at the Joint Research Center at Ispra near Milan. And I must say I learned a lot from him. Then there are these other papers and some more recent papers of 2019. So I hope I've taken you through some basics. Thank you very much. Okay, sir.